This is video help for the fourth problem in lecture 31. This is hard for you to perhaps read, but you've got these notes in front of you, so you'll know what I'm talking about. These are the multiple choice problems. Number one, trust your general theorem as if everything were squished to a point, the center of mass point, then the net force on the whole system will be just the total mass times the acceleration of the center of mass. Whatever system you look at, whatever number of carts or whatever you look at. Number two, look at the total energy. You've got, kinetic energy plus potential energy. You're instantaneously doubling this guy. While this guy then, right at that, you're still at that same point R, so this stays the same. So now you know the total energy, and that'll stay that total energy forever unless you change it from outside. In problem 3, just look at this support bar. You got something pulling up, you got something pulling down. How many somethings have you got pulling down? What is the force that each of these is pulling down when you neglect all the masses? The tension's the same all the way through this rope down below the support bar. Number 4, if this, block 1 is accelerating downward, if that's accelerating downward, then you know that first pulley, for example, is angular acceleration is this way. That means that the net torque has to be that way. There's a torque on this due to the tension on both sides. If this has to be, if I called clockwise positive, so that had to be 0, then you know how the tensions are related. And it's the reverse for the acceleration going the other way. In number 5, if I've got Papa Bear, I'm not going to draw a nice picture, but Papa Bear with a certain center of mass at the top and Papa Bear at the bottom, same center of mass, you're interested in the change in the center of mass. It's the center of mass up here and up to the center of mass here. Number 6, when rain is falling, this is horizontally, just like, forget the vertical motion. I'll tell you why in a moment. But this is just like an inelastic collision where the cart is coming sailing along and goes smash into a bunch of water that has no horizontal motion, no horizontal momentum. Inelastic, completely inelastic horizontally. So use momentum conservation, but not kinetic energy. So you're going to get some information there. And you can use that information to think about the final speed of the cart and water system and the final kinetic energy. By the way, for the vertical part, the vertical momentum of the rain just goes splat. It's not conserved. It's just absorbed by the cart. There is a normal force up and down. And it adds nothing to the kinetic energy because of that. It's like losing energy to friction. So the vertical part you forget about. You forget about its momentum and you forget about its kinetic energy, just vertically. Number 7, just go back and review your formulas for a rocket that's accelerating by ejecting mass. Number 8, remember your theorem, another squish theorem. Let me draw the thing. If I'm talking about something rolling, remember that what you've got are things like, F net is ma center of mass. The acceleration is of interest here is the acceleration of the center of mass. That's the thing that comes into Newton's second law for our squish theorem, overall general theorem that we actually use in number 1 also. So it's this point going in a circle, and it's its velocity. It's as if everything were squished to that point. In number 9, you're watching that same point too. You're watching that point move to a lower elevation, and you're interested in the distance, the difference between those two elevations, those two heights of the center of mass. Number 10, you've got an axis perpendicular to the paper here, P, and then an axis right through the center of the rod. And of course, this is classical, the classical parallel axis theorem. I've got two parallel axes, and I can relate the moment of inertia here to the center of mass guy here. And you can look at the theorem and decide how general it was in terms of whether you put this parallel axis over here or here or here or here or anywhere. All that you need to know for sure is the distance between those parallel axes. Finally, number 11. Well, the only thing I'll say here is, I got to have something turning it in a circle, something turning her in a circle, and I have to have something holding her up from sliding down. There. I hope I didn't give away too much, but helped save some time and clarify things.